Okay, so let's take stock of where we are. So if we're studying this format of oriented path, we're going to assume that we want to that's 0. And then if we had a steady C structure, let's just see that we need to compare C2 bundles and Fredholm multiplication. We get the Seiberg-Witten map. Seiberg-Witten map, which map the configuration space, which remember was L21 connection, spin C connections, positive spinners, and maps through and these yes, Seiberg-Witten map of A and B was of A minus quadratic in sigma, Dirac operator coupled to A, coupled to B, and then to stage fixing. That's your reference connection, and you know this is proper effect on that. Smooth proper effect on that. And it's and you want to be very equitable. So in this study, you want to just acted by scalar multiplication spinner. So this the quotient space minus V1 actually, what does it look like? So kind of picture of it is that there's the connection part. That's acted on trivially, and then there's the sections of S plus, but that's acted on non-trivially. This is some in our completion, it's some infinite dimensional complex Hilbert space. So this quotient you should think of as some kind of home on CP infinity. And if I look at the quotient, where I take the complement of where I remove the fixed point set, which is the cone point, or removing the cone point everywhere. This guy looks like zero infinity defines CP infinity some real Hilbert space. This is so the algebraic topology is very simple here. There's a CP infinity that's governing story, and I should say, let me just add here smooth proper orientable Fredholm map. And the orientation is provided by orientation of H positive. Okay, and then we observe that the kind of all this stuff is mapping to V of S under the Seiberg-Witten map. And if we look at the pre-image we look at the set of configurations that solve the equation. This is a turns out to be a smooth submanifold. Map of index B of S plus 1 with B of S 1/4 C1 squared of S equals 2 pi C sigma. All right. So inside here, there's this not inside the quotient, but this thing inside the inside this C1, this is the smooth submanifold. C1 and yes, but that's so here I've gotten rid of the Dirac equation and the map to sections of the plus sections plus these of one forms. That's the remaining two equations. It's still a proper Fredholm map of our oriented map. Same thing. So finally, we can define the Seiberg-Witten invariants if we take so, and we noted that if p plus of x is bigger than 1, then for numeric eta section and plus the image of this guy, which fits inside here, it's already solving the Dirac equation, but now it has to be if eta for the curvature equation and the gauge fix, this is the fixed set. So we get this Seiberg-Witten moduli space as G, S, and eta. This preimage, but divided by S1, and finally into this picture, it's sitting somewhere inside here, away from this fixed point set, so it's defining a homology class. It's a submanifold. It's defining a homology class. It's an oriented submanifold, and then we finally get our Seiberg-Witten invariants. Function of spin C structures to the integers and Seiberg-Witten invariants of S is the evaluation of C1 of the topological bundle on moduli space. That's G8. It's that if the address is vegan, 0 otherwise. Well, even greater than equal to 0 and vegan. Okay. But yeah, so so we want to, this lecture I'm going to try to develop some properties of this invariant and use these moduli spaces to prove some other theorems. But that's the shape of the invariant. I think the first thing we're going to do, although the invariants are defined when b plus is bigger than 1, it turns out to be really interesting to think about the opposite, most opposite case. Think about when b plus is 0 for a bit. So, so what we're going to do with these moduli spaces at the moment is reproof Donaldson's diagonalization theorem. But we're still going to use these moduli spaces, but in a situation where there's no invariance. But it's still interesting to think about them. So we're going to look at the case where b plus is 0, and so we should think about what. Yeah. So let me state the theorem. For Donaldson's theorems. '82 says that if Q of X, so if Q is, we're going to say negative definite. Obviously, it doesn't matter because you can change the orientation, but if it's negative definite, symmetric bilinear unimodular form, and Q is Q of X for a smooth form manifold. Then Q of X is isomorphic to the trivial diagonal form with all -1s on the diagonal. Okay, and what's the secret sauce? So what we want to do is, well, let's think about the dimension formula here for these moduli spaces in this situation. So so if b plus equals 0, then that means that polar characteristic of X is, well, it's 2 times 2 plus b minus of X, say H1 is still 0. And the signature is minus b minus of X. So so 2 pi plus 3 sigma is it's 4 minus minus b minus. So d of S is then 1/4 C1 squared of S minus plus b minus of X, because there's a minus sign there. And now something quite interesting is happening here when we think about it. So remember, the manifold is negative definite. So this is negative. C1 squared is negative, right? And C1 is also, C1 is just congruent to W2 of 2. So so remember, for characteristic vectors, their square is equal to it's congruent to the signature mod 8. Right. So one observation is that this is an even number. Therefore, because this is equal, it's congruent to the signature mod 8 because it's negative, definitely. Right. Yeah.
And just on the numbers, don't you have a what happened to your form?
plus one,
Plus
minus one.
-1.
Thank you. Yeah, good, good. Minus one is there. It's now not. I mean, yeah, sorry. The thing that's going to play a more important role is the DFS plus one. Which is the dimension of. Sorry, yeah. Good, but yeah. Anyway, okay, so this is negative. And so obviously, like most vectors have very negative square. And getting it close to be close to B minus is not easy. So if you notice that if Q is this guy, then the vector that's all ones, it has the property that C is minus. Let me start calling it B2 because it's all there. C is minus B2. In that case, this is 0. Right? But suppose if Q is maybe E8, again, with our convention that it's negative definite, well, then C equals 0 will do, and C is 0, and well, then great, then this number that would be 0, that would be 8, we get to, right? Positive, right? If Q is E8 x and minus 1, then well, then I can find a vector with C was is minus 1. That's coming from this side, and it turns out that it's a theorem of Elke's that in fact it's a characterization of the diagonal, the trivial form, that it's the only one that has characteristic vectors with square in absolute values of rank. Okay, so if Q was S buff, then well, the characteristic. No, sorry. There exists C characteristic such that C squared C dot C, let's say the absolute value, is less than the rank of Q if and only if Q is not a significant to the diagonal form. Okay, so that's telling us, when I think about the dimensions of the moduli space, is something very interesting. It's telling us that the only case in which I have a positive dimensional moduli space is if I have a four manifold negative definite intersection form, the only time I could possibly have a positive dimensional moduli space is when the intersection form is not diagonalizable. Right? So when the Seiberg-Witten equations came out back in '94, I think everybody figured out the proof of some version of balance theorem immediately. And I was walking down by the halls at Harvard at some point and ran into Noam and said, "Hey, you know anything like this?" And he said, he looked at me. "You don't know anything about modular forms, do you?" And the answer was no. But then he quickly provided that very beautiful and simple proof. Okay, great. So, okay, but now, so let's think about the consequence. So suppose proof of the Fredholm theorem. So suppose there exists 4 with negative definite and QX not associated to the diagonal form, then there exists this C characteristic such that C squared at absolute value with less than the rank. And then we take the correspondence in the C structure.
You want to it's not isolated.
So, sorry. Take S with C1 or less to C, and then we're going to consider this Seiberg-Witten moduli space. Yeah. All right. Yeah. Sorry. We're going to consider this moduli space, which is the 2 quotient version of it. I have a quotient not by the S1 actually. But we know that for generic eta, this is a smooth P of S plus 1 manifold, and that's greater than 1. P of S is positive. Right. And now this is a negative definite manifold. So it's a negative definite manifold. So the other thing we notice is that the equation F plus A equals eta always has a unique solution. Right. It's negative definite, so there's no B plus, there's no obstruction to solving this equation. So in particular, there exists a this is in the solution, let's call it A1. A0 is a reference guide, so this is A. And this is in but so what we've got, so this is our Seiberg-Witten moduli space, and it has a U1 action on it, and it has a unique fixed point. Orientable 2D plus 1 manifold having a unique fixed point on an S. Free except for this 1 point. That is not something that exists in this universe. So, right, and I don't know what your favorite way to argue it is, but if I take the complement of a little neighborhood of this guy, that's a sphere with free circle action on it. Quotient is a projective space, and that projective space, that CPM, bounds what they got. So, that's impossible. Such, don't exist. That's our contradiction, and it's quite a beautiful, simple application of the fact that we have these modular spaces around. Okay. Yeah.
If we start, so if X was actually negative, then
it is negative.
sorry, if X was like the sum of CP, then
Then
the
it would,
moduli space should have dimension like
no, well, this one. So this moduli space. Would have, this moduli space would have dimension, right. Did I see that? Yeah. Yeah. That moduli space would have, formally would have dimension one, but you should think that dimension one is really the circle action. So it's really, you know, you should think that it's a point with,
is it not transverse?
no, it's, I mean, the point is that when you realize this was plus one. That's what sorry. Yeah, this was plus one from the right.
Oh, ds is that minus one, so ds plus one is that.
Sorry, what?
There, I think.
Yeah, right, sorry. Yeah, sorry, yeah. So we were looking at the with dimension of the four lectures talking about Boeing.
I think my confusion maybe resolves when the one in the corner is actually zero.
That and this one.
That yeah, I think the current version.
Yeah, good. Yes. Right. So yeah, so for yeah. So for if it was just a connect, the intersection form is the trivial one, and this I can get this to be zero. So the dimension is minus one. And what the explanation for that is that there are solutions, it's just that there are always reducible solutions no matter what spin C structure you have. Right. And then you don't get a contradiction in if it's negative, you don't get a contradiction. And if d of s is minus one, the only thing you have is you just have that one fixed point as the solution. There's no other solution, so no contradiction. The contradiction only happens when there's a positive dimensional moduli space. So okay, all right. So let's go back to this. Yeah. So a bunch of little things that we should know about them. So I'll talk with Seiberg-Witten Invariants. So again, three plus of x is bigger than one. The first property is finite support. And what's the proof? Well, the dimension of the sub-Witten modular space is C1 squared of x minus 2000 minus 3 sigma. That has to be greater than or equal to 0. And C1 squared of s must be bigger than 2 pi plus 3 sigma. On the other hand, so proof A and B is that we have from the energy identity, in solution, we have this bound. Yeah, L2 norm is bounded by this stuff, but on the other hand, C1 squared, so there's a negative sign here. C1 squared is bounded above, but bounded below by this guy in order for the invariant to possibly be non-zero. But here, the curvature of the connection, L2 norm, is bounded by minus C1 squared and stuff. So that implies that some constant depends on x, g to the eta, and then plus 2 pi squared, 2 pi plus 3 sigma is greater than 1 and f(x) squared. So that's telling us that this is telling us that this is a representative of C1, and it gives an upper bound for it. That implies that for some choice of norm on the homology, the norm of C1 of S is finite, which is telling us that this guy has finite support. Okay. Another important property that's going to come up. So there's another symmetry of the equations. This conjugation symmetry. So if I have a spin C structure with Clifford multiplication and spin bundles, then conjugate spin C structure where the Clifford multiplication is the same map, but I just think of taking the complex conjugate bundles. That's fine. But that's a different spin C structure. It's determined as an opposite sign. Right. And you can check that this preserves solutions. So, kind of can use this Seiberg-Witten map. So that says two different interesting things. This, if this spin C structure is not isomorphic, this one, it just means that two different spin C structures that have the same answer, right? On the other hand, this spin C, the conjugate spin C structure might be isomorphic, in which case it's actually a symmetry of the Seiberg-Witten map. So if and that exactly happens. So when it's a spin structure, if S comes from a spin structure, S bar is isomorphic to S. Well, really via basically like quaternion J. And in fact, you can take what a spin structure is a spin C structure together with a conjugate linear isomorphism that in dimension 4 squared to -1. So consequence that SW has the property that W of C is equal to plus or minus x W of C conjugate, and the Seiberg-Witten map, trying to help out at least, Seiberg-Witten map, help out kind of thing, but at least the tiny bit, is J equivariant. That's the distinct structure. So the already was S1 equivariant, so there's an action, it's now P2 equivariant, and that's going to play an important role, I think, in Genfeng's lectures, if he manages to get there, now that I've left him way too much to do. Anyway, so there's a really interesting, very deep story. This is where the proof of Brutus pennies that theorem comes from, and Genfeng versus the Hopkins sheet about at all. Get a little more juice out of that. Yeah, so I'm going to finish up with is try to get you, let's see, finiteness. Yeah, okay. What I want to finish up with in the last few minutes is to take a look a little bit at the case of theorem manifolds. We've got these invariants. What the heck do they mean? Can we ever compute them? Right now, it seems quite hopeless. When it first came out, it seemed quite hopeless, but actually, it didn't mean quite hopeless then, because already Witten's original paper make the following observation. So we've got now X is a Kähler manifold, so it has a whole bunch of stuff. It's got a complex structure, not to be confused with that. I don't know why they do that. But it's called J. It's got a Riemannian metric, and it's got a symplectic form, and these guys are so. This is supposed to be integrable. It's really complex coordinates. This is a symplectic form. And amongst that, J and omega are both supposed to be parallel to the Levi-Schmidt connection, transforming the Levi-Schmidt connection, et cetera, et cetera. So all this great stuff. And in particular, one nice thing to notice is that such a J determines a spin C structure. So remember, if I have the J, then the classified tangent bundle splits into a 1, 0, and then 0, 1 piece. And this is like, if we're complex coordinates, this is BZs, that's the BZ bars. So the complexified exterior algebra decomposes the EQ decomposition, and we're just in dimension 4. And what we're going to look at is, so an important character in this complex geometry is that this is a canonical bundle. And call kx. It's a bundle of zero forms, so in dimension 4, those are things that look like this. And yeah, a few interesting facts. If I look at C1 squared of kx, what is it? There's 2 pi x plus 3 sigma. And by the way, for the algebraic topologists, this is the first Poincare eigenclass of lambda plus. Okay, so and furthermore, indeed, lambda plus is multiples. So yeah, so let's just think about this for 1 second. If I write this guy out. The next one, if you roll 2, that's dy 1, which dx2. The thing to notice is that if I label these guys instead 1, 2, 3, 4, so that's the orientation convention, but that's the complex convention. Right? Label these 1, 2, 3, 4. This is 1 through 1, 3, 2, 4. This is 1, 4, 2, 3. These are both self-dual forms, right? And of course, the Kähler form is also self-dual. So, in fact, this isn't so surprising. Lambda plus is isomorphic to the 2 multiples of the Kähler form plus the canonical bundle. Okay, now, and remember that for the canonical clusters, that's adjunction equality for complex curves. It's very important. And we'll notice that a spin C structure is a lift in dimension 4. You should think of a spin C structure as a lift of a 2-dimensional homology class, characteristic 2-dimensional homology class, for something a little more interesting. And so what we're going to do is define S plus of J as that's this vector bundle. Notice that this is the inverse of the canonical bundle, dual of the canonical bundle, and S minus is this 0, 1 forms. That's great, but now we need to have Clifford multiplication stacked on. How do we do that? Well, we remember that this is complex geometry, so there is an operator d bar with 2 bar star, which maps sections of this guy, sections of this guy. And I mean, I can do this for all forms, and for the next equation, put it that way. And it's a standard fact. The Kähler identity comes with the square of this operator. Again, we should really think of that in all complex forms, but square of this operator is 1/2 the Hodgson Fossa. Now, who cares? Why do you care? Well, let's think about the symbol of this operator. Okay, the symbol is what? It's symbol of an operator. What does it do? It maps the cotangent bundle tensor the domain to the range. Range vector bundle, right? So that's T star X, then say what I want to do. I'll plus the T star X, what I call that's minus. Oh. That's great, right? That's the kind of thing we want for, you know, for the Clifford algebra. That's going to be the interesting part of the math, and then the Clifford, as long as we need to check what if we call that C, that's the beginning of it. So what we should check is that the C conjugate composed with C, what is it? But symbols, it's the symbol of a composition is the composition of the symbols. So this is the symbol, the symbol of the quantity, which is minus a half on a cotangent vector theta minus a half on the length of that cotangent vector. So on theta. So that's so this wasn't the right thing. That's not quite right. It shouldn't have a half. So what we should do is define C to be the square root of 2 times that. Then we get a 2 and we get the right answer. So this is so a little thinking, further thinking along these lines tells you that in fact we've constructed a spin C structure that we do its vector bundles. I told you what Clifford multiplication is, and the Dirac operator for this spin C structure is square root of 2 times d bar star. So that's great. And now for any S on X G is of the form this that's equal to Sj tensor some line bundle E, and the Seiberg-Witten equations look nice in this setting. So so in particular S plus tensor E, that's that's the sections of E plus 0,2 forms with values in E, etc. And what do I want to say? Yeah. So if we have the section of S plus tensor E, then we can write phi as an alpha and beta, where alpha is in here and beta is in here. And with respect to this decomposition, the Seiberg-Witten equations look quite nice. I should say also, yeah, so now V is going to be a connection in E. All right, so I've got already a connection. Sorry, I should have said it. These guys already have the Levi-Schmidt connection, right? And it turns out that that's a spin connection when we go through this story. So that's something you have to check. And then to get a general spin connection in this tensor product, I need to pick a connection with E. And now, by the way, what's the determinant of this Sj? Well, the determinant is the determinant of S plus, so it's go to 0, but it's the inverse of the canonical bundle. Yeah. And yeah. So we should think about what the equations look like in this situation. So first of all, observation, what's the dimension of, dimension of Sj is what? Remember, its determinant is this guy, square of this guy is still there? There it is. It is that. So the dimension is 0. Okay. And if I look at the dimension of Sj tensor E, a little computation shows you that it's C1 of E minus C1 of a X times C1 of E. You know, the value of Masterclass. That's what the dimension formula simplifies to in some sense in this situation. So you notice that C1 of S, sorry, I should have said C1 of Sj tensor E. That's a if I tensor, if I take the determinant of this guy, I get there's still minus AX, but then I get 2C1 of E. So if I plug this into the dimension formula, I get this, and this is the dimension of the Gromov pseudo-homomorphic curve modular space for the Poincare dual. The pseudo-homomorphic curves in the homology class Poincare dual to E. Okay, so we'll see that seems so. This is hinting to the fact that the Taub's theorem that the Seiberg-Witten invariants of a symplectic manifold are equivalent to the Gromov-Witten invariants. Okay, that's the first hint of that fact. And what else did I say? Yeah, and you notice that there's a symmetry here. If I replace E by Kx tensor E inverse, this is preserved. This number is preserved. You can check that. That makes sense because if I take this guy and tensor this thing with it, it just switches the order, right? Because the K cancels with this guy, and yeah, and yeah. What did I say? Yeah, not what I think about. Anyway, but it's invariant under this thing. This is the Kähler version of the J symmetry. Anyway, so The. What about the Seiberg-Witten equations themselves? So the game here is that, so this sigma phi, it turns out to be it turns out to be this gadget, so this is times omega. So remember, subtle forms decompose into multiples of the Kähler form, and then the real part of 2,0 or 0,2 form, however you want to say it, and we want we want something imaginary, so this is really the imaginary part of it. If you think about this formula, the E bit cancels. Like this guy was in K inverse tensor E. Alpha itself is in E. So this thing, when I conjugate it, it's in E inverse. So this thing is in K inverse and the 2, 0. Okay. No.
Well, wait, I find better.
Oh, sorry. Right, so alpha and beta are the two components here. Right, and if I take this guy, if I take the conjugate of this guy, that's not doing anything, but that's changing E to E inverse. And so if I take the conjugate of this guy times this guy, it cancels the E's and just gives me a 0,2 guy. Right, so that formula makes sense. And yeah, great. So the Seiberg-Witten equations are equivalent to three equations now. So so here, what I remember, we're allowing a perturbation eta, but I'm going to decompose eta into a bit along the symplectic form. This is just a projection of f along the symplectic form. So this is an equation for functions. I've gotten rid of the omega here. So this is just an equation for functions. This is an equation for 0,2 forms. And the key proposition is that if any solution to the kappa equals 0 version has v bar alpha equals 0, v bar beta, v bar star beta equals 0, and alpha beta equals 0. So that's a strange and perhaps surprising conclusion, but it's telling you that only one of these can possibly be non-zero, right? And say if beta is 0, then sorry, and I should say, yeah. So for F02 of B equals 0. So this is telling you that B is defining a holomorphic structure in the bundle E. Kappa 0, alpha and beta are the product is 0, so the 0,2 part is 0. So alpha is a holomorphic section of a holomorphic line bundle, right? And but you notice that only one of alpha or beta can be non-zero at a time. But if the Seiberg-Witten invariant is non-zero, then there must be holomorphic section of this line bundle, and sorry. So let me just state one corollary of this. So by the way, the proof of this is not very hard once you stare at these equations. If you stare at this equation for a little while, you decide I should try and take d bar of this. Now, d bar squared is f02. So that pops back into this equation to give you normal alpha squared times beta, and then plus Laplacian of beta, and then little integration by parts gives you these two, and then taking d bar star of it gives you the same thing. So it's not very hard to prove this. Let me finish by giving you what eventually the corollary is. So by the way, it turns out that solving so if I have a holomorphic line bundle with a holomorphic section, the first two equations are solved. Right, I just have to solve the last equation. And the only obstruction to solving the last equation is checking a sign. So that's it's called the remaining equation is called the vortex equation, very well studied PDE. So kind of generalization of the prescribed scalar curvature equation, comes out one equation, dimension 2. But in any case, eventual consequence of all this is this beautiful Seiberg-Witten is b plus x Kähler b plus of x bigger than 1 in complex geometry. That means PG is positive, that implies there exists a holomorphic section of magnitude 0. PG is the dimension of magnitude 0, and Kähler manifold process 2PG plus 1. There's just a holomorphic section, and then the basic classes, basic C structures, in C structure pushed in various are non-zero, come from being able to factor the canonical bundle as E tensor F as holomorphic bundles. And then Sj tensor E and Sj tensor F are holomorphic bundles with sections. Let's say little e and little f, then E times F is section K. Right, so if I can write the canonical bundle of the tensor product of holomorphic bundles with holomorphic sections, then these guys are have a Seiberg-Witten invariant 0. And in fact, that you can often you can just compute the Seiberg-Witten invariance from this picture. It's often pretty easy, so you can compute it for elliptic surfaces where you understand the canonical bundle very clearly. You can compute it, say, for torus cross a Riemann surface, and lots of examples you can get for this. So maybe I should have stopped.